Okay, folks, let's take a look at forces at an angle problem. Here we have a 50.00 kilogram toboggan being pulled by a force of 180.0 newtons, but it's at an angle of 32.0 degrees. The coefficient of friction is given to us in this problem as 0.255, and we want to find out what the acceleration of the toboggan should be. So we should start off by doing a free body diagram, which technically is just a dot with the forces that are applying to it, kind of coming out from there as arrows. I'm going to draw as a box just to give myself some space. So I'll start off with my toboggan. Here's my box of everything. The mass is going to be 50.00 kilograms. And take a look at some of these sample forces that are acting on it. So we'll have gravity pulling down, F sub g. We'll have the ground pushing back up as a normal force, F sub n. Our applied force, F sub a, which is given to us at an angle of 32.0 degrees. And I'm going to resolve into its two components of FA x hat for the x-axis and the FA y hat for the y-axis. And we're also going to have a force of friction, which is going to oppose any potential motion that should happen in this problem, F sub F. So now we have our forces laid down. We should probably put in some sort of net force equation. There's two ways to look at this. Net force, F net, as mass times acceleration. We do have the mass, but we are trying to find acceleration in this problem, so it's no use to us as of right now. So we're going to use the sum of forces version. And I'm going to break it into the x and y components. So I'm going to have the sum of the Fx, there we go. That's our x forces. And I take a look at my diagram and ask myself, what forces do I have acting in the x-axis? I have the Fax component and the Ff. So the two of those, Ff plus Fax, will add up to give us our total net force in the x direction. I'll do the same thing for the y components. There we go. Y forces. And here I actually have three. That's gravity pulling down, the normal force up, and the applied force in the y direction. So I'll have F sub n and F sub g, oops, and our Fa y component as well. So there's our forces as a sum of. And last we should probably do now is start to take a look at how to do some calculations. Everything is outlined for us, so we'll start off with the easiest one, which is the force due to gravity, which is our mass times acceleration due to gravity. And we'll put that down as 50.00 kilograms multiplied by negative 9.81 meters per second squared. And we're assuming it's negative 9.1 meters per second squared, although we know it does actually vary. And that's going to give us a value of negative 490.5 newtons. Now I can find my two components. I had them up here, Fax hat and Fay hat. This is resolved into a right triangle, so I can use some trig to find out what those values are going to be. So I'm going to jump with the Fax first. So Fax. And when I take a look at that, I notice it's in the x-axis, and it's going to be an adjacent to this angle. So I'm going to use cosine. So Fa times the cosine of my angle theta. In this case here, we're going to have my 180 newtons multiplied by the cosine of 32 degrees. Make sure in your calculators that you have it measured in degrees, not radians or gradians. And that gives us a value of positive 152.65 newtons. There is more digits you can work with, but really having a couple past decimals is going to be enough for our purposes. And I go to my y component as well. Fa, and this time I take a look, and that's going to be the opposite to my angle of 32 degrees, so I'm going to use sine in this case. The sine of 32 degrees. So I plug it in, 180 newtons times the sine of 32 degrees. And it gives us a value of positive 95.39 newtons. Now, it is quite important to actually acknowledge that it's going to be in the positive direction because it is a pull. And that's one of the things we have to focus on in this problem, because when you draw your applied force, I put it at an angle going up. Now, if this is a push, it would be going down, which doesn't sound like a big deal, but it would involve the Fay component being negative instead. So now I have my force due to gravity, my applied force in the x and the y directions, and I need to find out what I can do from here. Now I have to rely on the equations I made in the first place. And this is going to be my net force, But I'm going to make an assumption here that the forces acting in the y direction are all going to add up to 0. And the reason I'm going to do this is because I can assume that the toboggan is just not going to accelerate off the ground, nor should it accelerate into the ground. So if you have no acceleration in your axis, you should have no net force. You just consider the equation you have to start off with. So if there's no acceleration here, if this is 0, regardless of your mass, you're going to have a net force that is 0. So that plays into our advantage because we do have our y component as Fa. We do have our force due to gravity, so I can find my normal force. So I'll move up here. Normal force, just rearrange that equation, is going to be negative Fg plus Fay. Oops, it shouldn't be plus, it should be minus. All right, negative Fg. We calculate that to be negative 490. So double negative is going to be important here. Minus our positive value, 95.39 newtons. And that gets us the value for a normal force, positive 395.11 newtons. Now with the normal force and the coefficient of friction was given to us earlier, 0.255, I can find out what the force of friction actually is. So F sub F is mu Fn, plugging my values here, 0.255 times my normal force that I just calculated, positive 395.11 newtons. Now we did say it was positive in here, but this is going to be a scalar calculation because you look at the force of friction in the x-axis and the normal force going to be in the y-axis. So even the fact that I put positive 395 here doesn't really matter. I'm going to plug in my values and I end up running into 100.75 newtons. So we're almost there now. I'm going to go back to our net force in the x direction that we have up to here towards the top. So this is now become important to us. Let's rearrange that because I do have my applied force in the x direction. I now have my force of friction and I want to find my sum of forces in the x direction. That is going to be my net force right there. So let's plug these things in. The sum of the x forces is going to be my FF, which I have in here. I'm going to put that as a negative 100.75 newtons. And the reason I'm going to say it's negative is because when I go back up to my original diagram, I take a look, the force of friction was written off to be in the left direction, whereas my applied force in the x direction is in the right. So those two should be opposite in sign. And since I designated the right to be a positive, then going off to the left should be negative. Your force of friction should always oppose any potential motion. So whatever sign you give your motion, the opposite sign should apply to your force of friction. So there's my force of friction, and I'm going to add it to my applied force, and I'm running out of space here, positive 152.65 newtons. Barely get it in. And we get positive 51.90 newtons. That actually means it's going to have some sort of acceleration, and how much acceleration it's going to experience is based on its mass. So the last thing we have to do is take my net force equation I had from above, m times a, and I can find my acceleration as a rearrangement. Net force divided by mass. Net force just recently calculated is 51.90 newtons, and the mass given in the original part of the problem, 50.00 kilograms. And I can plug these things in and find out that I have positive 1.04 meters per second squared. So that's going to be my answer. So the object is going to move. It is going to experience a positive acceleration of 1.04 meters per second squared. I'll take a look at my sig figs to make sure I'm good that way. The measurements that I have, 50.00, there's 4 there, 4 and 180.0 newtons, but there's only 3 here in 32.0 degrees, and there's only 3 here as well in 0.255. So I am going to use just 3 sig figs. My answer, 1.04 meters per second squared.